Examine the function f of x equals 2 root x minus x for the following properties and use that info to sketch a graph. If we look at the domain, we notice that we have a square root of x here, so that restricts our domain to the interval from 0 to infinity, including 0. So we're not going to have any negative numbers here. For intercepts, for the y-intercept, we just plug in 0 for x. And when we do that, both of these terms go away. So we get 0, 0 as an intercept. That'll be both an x-intercept and a y-intercept. For the other x-intercepts, if there are any, we need to set this equal to 0 and solve. So we would want to know when 2 root x minus x is equal to 0. If we add x to both sides, that gives us 2 root x equals x. And if we square both sides, that gives us 4x equals x squared. And this is something that's a little bit easier to work with because we're used to solving polynomial equations. If we subtract 4x from both sides, that gives us 0 equals x squared minus 4x. We can factor out an x. And we can see that in addition to x equals 0, which we've already seen as an intercept, it looks like we might have x equals 4 as an intercept. And in fact, if we plug in 4 to the original equation, we will see that we end up with 2 times 2, which is 4 minus 4, does equal 0. So our other intercept is going to be at 4, 0. So we've got 2 x-intercepts, one of which also happens to be a y-intercept. There is no symmetry here, especially because this function is not defined for negative values, so we don't even have a left-hand side of this. There are no obvious asymptotes. The square root of x and x are both functions that aren't known for having asymptotes, so we are not going to worry about that. For the next couple of bullet points, the intervals of increase and decrease and the local maximum and minimum values, we will need to differentiate this. So let's get the derivative. If we are taking the derivative of the square root of x, remember that's x to the 1/2, and the derivative of that is 1/2 x to the negative 1/2, or 1 over 2 root x. But if we're multiplying that by 2, the 2's cancel, and this just becomes 1 over root x, then minus 1, because the derivative of x equals 1. If we want to know where this is undefined or where this equals 0, it is undefined when x equals 0, because we can't have a 0 in the denominator. So one of our critical numbers is 0. That's also an endpoint, so that is already a curious point. And then also, we want to know when this equals 0. Well, this equals 0 when 1 over root x equals 1, and that's going to happen when x equals 1. We can see very clearly we would need x to be 1 for that equation to be true. So our critical numbers are going to be at 0 and 1. And remember, 0 is an endpoint of the domain, so we don't have to look to the left of that. And we've got 1, and let's see. We can rewrite this derivative if we want there to be factors. We could put it all in one fraction, 1 minus root x over root x. So our factors are 1 minus root x and root x. If we look at root x, that's always going to be positive. And then 1 minus root x, if we pick a number between 0 and 1, this square root of x is going to be less than 1, and we're taking 1 minus something that's less than that. So that's going to still be positive, but when x gets bigger, that's going to be negative because we're going to be subtracting something that's bigger than 1. And so our derivative is going to end up being positive and then negative. So we're increasing and then decreasing, which gives us a local maximum when x is 1. And if we do plug that into the function, that's going to give us 2 times 1, which is 2, minus 1, which is 1. So that's going to be at the point 1, comma 1. All right. For concavity, we need to find the second derivative. And so we need to differentiate the first derivative, which we've got right down here. The derivative of a constant is 0, so we just need to differentiate 1 over root x. That's the same as x to the negative 1/2 power. The derivative of that is going to be negative 1/2 x to the negative 3/2. And that is the same as negative 1 over 2x to the 3/2 power. And remember, our function is only defined on the domain from 0 to infinity. This is going to be undefined at 0, but if we look at the rest of this domain, whenever x is positive, x to the 3/2 is positive, which means the denominator is positive, which means the fraction is going to be negative because of that negative sign out front. So this is always going to be negative when it's defined. It's not defined at 0, but that's fine. Everywhere else, this is going to be a negative second derivative, which means we're going to be concave down on the whole domain. Okay? So let's use this information to try and sketch the graph. We know that we have an end point when x is 0, and that's going to be at 0, 0. So this is going to be the end point of our curve. We also have an intercept at 4, 0, and we have a maximum at 1, 1. And if we look at what's happening to our function, it's increasing between 0 and 1, and then decreasing afterwards. And it's always concave down. So for us to be increasing and concave downward on that first interval, it's going to look something like this. And we know we're going to have a horizontal tangent line there because that's a local maximum. So then it's going to start going downward, and it's decreasing and concave downward everywhere else. So it's going to look something like this probably. Excuse the wobbling of my hand. If we wanted to have more accuracy down here, we could pick another x value and plug it in. In fact, why don't we try that? A nice x value here is actually going to be 9, because if we plug in 9 for x, we can take the square root of 9, which is 3. So this is going to be 2 times 3, which is 6, minus 9. 6 minus 9 is negative 3. So we actually have a point at 9, negative 3. Not too far off what we had, but if we want to make this nicer, we can go in and we can subtract this and redraw it so that it goes through that point. Let's give this a try. It's going to look something like that. And that is our graph. We've got our intercepts, we've got the maximum value, we've got our concavity and our intervals of increasing and decreasing, and we're good to go.